And now chemical stoichiometry. First of all, a little warning, the lesson here presumes that you've done the grilled cheese stoichiometry section, so we assume that we've already talked about the process of writing the 5 steps for writing a recipe, identifying A and B, etc., etc. So if you've not done that, either you're going to need a different lesson that does not assume that, or you need to go watch that lesson first. So here goes. Stoichiometry with actual chemicals. So here's a problem. How many grams of carbon dioxide is made from the combustion of 25.0 grams of butane in excess of oxygen? Interesting. Wonder why the word oxygen wasn't on there. So, that'll fix that. You were taking a long time to write it down anyway. They'll just give you a few extra seconds before you have to pause it. Yada, yada, yada. Boom, go. Step 1. Well, in the grilled cheese lesson, the first thing we needed was a recipe. So, in a chemical situation, you're not going to call it a recipe anymore. You're going to need a balanced chemical reaction. So, what we'll see is these steps are exactly the same, but with little changes here and there. Instead of a recipe, we now need a balanced chemical reaction. That is our new recipe, is the balanced chemical reaction. So our first step in this problem is going to be, we need to write a reaction for the combustion of butane. Now it may be helpful to brush up on some of your reactions, but that's not the purpose of this lesson. So we will presume that you know how to write reactions. So combustion, remember with butane you start out with the formula of butane, which you might have to look up, but there it is, C4H10. Combustion is always going to burn things. To burn things you need oxygen, and you always, when you burn a hydrocarbon, are going to make the same two things. You're going to make water and carbon dioxide. And I'll let you pause it now for a minute and practice balancing. Go. Nope, pause it, I said. Balance it. You got to balance it. You can't do this if you can't balance it. Okay, thank you. Thank you for pausing. Unpause it when you have it balanced, and we'll check to see if you got it right. Oh, good. You got it right. Just kidding. So those are the correct coefficients whenever you've balanced it. The combustion of butane, 8 carbons on each side, 26 oxygens on each side, 20 hydrogens on each side. So we're good. So that's a balanced chemical reaction. We've done that. Step 2. Identify what you know. This is exactly the same as grilled cheese, by the way. A, what you know. B, what you want to know. Identify A and B. What do you know? What do you want to know? So if we go back to the problem, how much carbon dioxide is made from the combustion of 25 grams of butane? So A, the thing we know, is of course the 25 grams of butane. Right there, A. And the thing we want to know is how much carbon dioxide. That is B, the thing we want. So butane is A, the thing we know.
Have your attention, please. The following.
Carbon dioxide is B, the thing we want to know. So I like to label these in the reaction. I find it helpful to actually work around the reaction whenever I'm doing these. So A, butane, the thing we know. B is carbon dioxide, the thing we want to know. So I would actually write those letters A and B above the chemical formulas for the things. So step 3. Just like with grilled cheese, we had grams. We need to get it into slices. Similarly, for this, we want to get our unit into reaction units. Doesn't matter how many grams, because our recipe doesn't talk about grams. So what is the reaction unit for this kind of a problem? Well, it's moles. Chemical reaction use moles. The ratio in a chemical reaction is not grams, it is moles. It's not slices, it is moles. So moles will be taking the place of slices and things like that from our grilled cheese. So we must convert not to slices now, but into moles. And if we know grams, G equals N times W. If we rearrange that to get N by itself, you'll have N equals G over W, where N is moles, G is the mass of the compound or element, and W is the molar mass off the periodic table. So, there you go. Find moles of A is essentially what step 3 is. Find moles of A using G over W. So let's do that here. Here's our reaction. A is butane over here. We've got our formula, moles of A equals grams over molar mass. So what are the grams? Well, we go back to the problem. We read that there are 25 grams of butane. We divide that by the molar mass of butane, which is 58.0. If you're not sure why that is, go back and count up 4 carbons and 10 hydrogens. Important note here, when I find the molar mass of butane here, notice that I counted up 4 carbons, it's 48, and 10 hydrogens, which is 10 times 1 is 10, that's 58. Notice I completely ignored this 2. We do not double the molar mass. Do not double the molar mass because ignore coefficients when you're calculating W. Do not look at the coefficients when you're calculating W. I cannot say that enough times. Do not count coefficients when you're calculating the molar mass. This W, you can cover up any number out in front. You do, of course, look at subscripts like we always have, but not coefficients. So that's where our 58 comes from. You divide those and you get 0.431 moles of butane. That's what we just found. So we found moles of A is 0.431. We've done step 3. We've got a reaction unit. We have 0.431 moles of that stuff. So step 4, just like before, is exactly the same. We're going to beaver over armadillo it. Use the coefficient ratio. Moles of B equals, to get the moles of B, we take the moles of A times the coefficient ratio, B over A, beaver over armadillo, not the other way around. The armadillo's hard shell will hold the beaver up without crushing him, so everything will be fine. That's your formula. Moles of B equals moles of A times coefficient B over coefficient A. And that is step 4. So there it is, kind of written within the steps. Same exact thing, nothing new there. So let's do that. What's that look like? Well, here's our formula. Moles of B equals moles of A times coefficient B over coefficient A. So moles of A we just calculated. It's this 0.431 number. So that goes in there. And we're going to take that times the coefficient ratio. Coefficient of B, right there. Coefficient of B was 8, so that comes down there. Over the coefficient of A, which we look up here, that is the 2. So 0.431 times 8 over 2 is 1.72. And what is that? That's moles of B. Moles of carbon dioxide. So we now know how many moles of carbon dioxide we have. We have 1.72 moles of carbon dioxide. So we're now at step 4. We've essentially, this is like sandwiches. We figured out how many sandwiches we can make, but that's not the question. The question is, the last step, of course, is we got to answer the question. Ooh, unfortunately, this didn't all fit on my screen. Answer the question is step 5. Let's see, can I move that? There we go. Answer the question. So we're going to move this down. Answer the question is step 5. Question is often, but not always, answered using the formula for mass, G equals N times W. So in this case, anytime it's asking for mass, you will use that G equals N times W formula. So we're going to answer the question here. So what was the question again? Well, our question was, how many grams of CO2 is made from the combustion of 25 grams, blah, blah, blah. We figured out the answer is 1.72 moles. We've got that. But the question is, how many grams is that? So we have to convert grams from moles. So how do you do that? Well, we use G equals N times W, where N is the moles, W is the molar mass. So we have N equals 1.72 moles. We're going to take that times W, the molar mass of carbon dioxide is 44. Where did that come from? Well, it came from the formula CO2. Carbon is 12, and there are 2 oxygens, each of which is 16, which gives us 12 plus 32, which is 44 grams per mole. So N times W is 75.7 grams of carbon dioxide, and that is the answer to the question. So there we go. The 5th step, we've calculated the answer to the question. 25.0 grams of butane, when burned, can produce 75.7 grams of carbon dioxide. And now you can do stoichiometry.